Hello everyone, I am Vamshi from EC department. My AAT Tech Talk topic is about evaluation of signaling loads in Node Stack 5G mobile network. Abstract. Present mobile communication system suffers from the exponentially increased mobile traffic and research on the fifth generation 5G mobile network architectures is ongoing to solve this problem. We investigate the feasibility of the proposals used for the network architecture evaluation from 4G to 5G and first propose a compatible network architecture which decouples the management plane, the control plane and the user plane based on no stack framework proposed in our previous study. We mainly design detailed procedures including UE attachment service request and dedicated bearer activation or deactivation for our proposal network architecture. Finally, we establish a clear analytical mode of the application and system states to evaluate the signaling loads of new architecture. Simulation results show that our proposal network architecture with elaborated signaling procedures as much impact on the total signaling loads of system and could obviously decrease the signaling overhead compared with LTE. Introduction. Mobile internet and machine type communications are recognized as the main driving force of investigating the 5G for future mobile network. There is speculations that the volume of the global mobile data traffic is expected to increase more than 200 times from 2010 to 2020, while the number of the mobile communication terminals will reach 26 billion in 2020. And the 5G network is expected to support a wide range of new services and applications with very diverse requirements, mainly including 3D video, Ultra HD screen, cloud computing, virtual reality, etc. These business scenarios need 5G network to provide higher traffic volume, low latency, the connection of huge number of devices, etc. In order to meet these challenges, 5G should not only improve the link capacities but also need a more flexible and scalable architecture with the introduction of new technologies. Network function virtualization and software defined network are two promising technologies to provide such flexibility, scalability for 5G network and are expected to play a significant role in the construction of 5G network architecture. The main idea of NFV is the decoupling of physical network equipment from the functions that run on them. NFV promises telecommunication service providers with more flexibility to expose their network capabilities and services to users and other services and the ability to deploy or support new network services faster and cheaper so as to realize better service agility. The figure shows general framework of no stack. No stack is the abbreviation of no stack. Not only stack. In no stack architecture, it pushes down the layer by layer protocol stacks and encapsulates all protocol layers as modules. The protocol stack is reserved and can be implemented by orchestrating associated modules. Further, we adopt SDN principles to decouple the control user managed plane function of each protocol layer. Thus, the protocol layers of user plane are flat, which can be reconstructed flexibly. The protocols of control plane are concentrated in the SDN controller so that the operators can control the network in a unified and coordinate manner. The management functions are communicate with control plane functions via the open north interface of SDN controller and is in the charge of the customized needs of varied business. Benefiting from these features, the proposed framework is very flexible and can support many new functions beyond conventional protocol stack. In this paper, we first propose a compatible network architecture which decouples the management plane, the control plane, and the user plane based on no stack, a software defined network enabled framework. And then we mainly make detailed procedures for the attachment, service request, and dedicated barrier activation or deactivation of for our proposal. Network. Finally, in order to evaluate signaling loads of the procedures, compare with the legacy long-term evaluation architectures, we establish a clear and analytical mode of the application and system states. Simulation results shows that our proposal network architecture with elaborated signaling procedures as much impact on the signaling loads compared with the additional LTE architecture, U or C or M decoupled architecture. To enable intelligent flexibility and network programmability inspired by no stack that explained briefly about, we propose a U or C or M decoupled LTE or EPC architecture. Our proposal, as showed in figure 2, follows the line with the software defined network principle and provides a high level functional view of novel architecture. We separate out control functions from the data forwarding functions of the SGW and PGW and combine the control plane functions of SRPG DW as well as user plane functions of SRPGW. As a result, the new XGWC X gateway control plane is centralized and runs on top of the global controller as an applications when the UX gateway user plane represents an advanced logical entity controlled by the XGWC in the global controller. Also, the mobility management entity core control entity in LTE is converted to an application that runs on top of global controller. The global network view module is a general database application. Similarly, we reconstruct the functions of the management plans functions into architecture. What's more, we replace the control protocols that run on S1 MME and S11 interface with the SBA protocol. OpenFlow is a popular protocol for the southbound interface and can be employed on the SBA. The global controller communicates to architecture by the NBI. The architecture is composed of the following entities. Global controller. Global controller is the main component of our architecture as it controls the user traffic forwarding plane of the evolved node and GWU. The global controller is responsible for user session establishment and loads monitoring on the user plane. Global controller is on OpenFlow controller and a collection of applications built on the top the global controller over the time, over the inner API or over the REST API. MMA is the main control entity for the EUTRAN. It communicates with a HSS for user authentication and user profile download and provides user equipment with evolved packet system, mobile management and EPS session map. Functions using non-access stratum signaling. In our architecture, the MMA communicates with the global controller using the controller intra API. The 3GPP interface between the MME and HSS is still maintained. XGWC represents the global control functionality of the SGW and PGW. It is responsible for resource management for bearer resources and IP address, tunnel endpoint identifier, assignment for GTPU. The XGWC allocates unique TEID value per session within S1U interface between ENet and GWC with the OpenFlow protocol. The global controller can set count errors for the number of XGWUS in order to get periodic load statistics. By comparing the received load statistics of the XGW compatibility, the global controller can easily get the load status of each XGW and therefore perform more efficient load balancing. XGW represents an advanced logical entity controlled by the XGWC in the global controller, and the advanced open flow switch that is able to encapsulate and decapsulate GTB packets can be enabled technology to implement logical entity. This switches applies the rules received from the global controller. It is responsible for packet forwarding between the ENB and PDN. ENB is an intersection point of the access network and a core network. It keeps the same radio function in 3GPP stands while is enabled with the OpenFlow protocol for data plane management. Therefore, the data plane is programmed according to constructions received from the global controller. ENB sends and receives user IP packets through a packet data convergence protocol and IP mapping table. When ENB receives IP packets, it checks destination's IP address in the downlink. If matching entries available in the PDCP and IP mapping table, ENB sends packets on the particular PDCP connection over the radio interface. In the uplink, packets are forwarded to the network through connected XGW orchestrator. In legacy LTE network, the PGW performs policy enforcement, packet filtering and charging based on the policy and charging rules provided by a policy and the charging rules functions. On preliminary stage, we consider reconstructing these management functions into orchestra. Therefore, when global control wants to obtain quality of service and charging rules for the XGWC, it could represent the unified RESTful API to architecture. Then architecture handles the request and response, sets the demanded QoS and charging rules into popular format such as JSON. LT based on no stack signaling flows. In this section, we describe briefly procedures related to signaling analysis based on our system model referred to the LTE standard. Input and use case is the UE or PDN originate the service. Before explaining these situations, it is important to show how UE is initially attached to the system and at least. We also describe that dedicated barrier activation or deactivation procedures as in supplement for service with QoS guarantee. In general, protocols of the LTE access network remain unchanged in the proposal. In contrast, the protocols related to network elements which are replaced in no stack architecture are redefined or delete. UE attached procedure. UE attached diagram shown in figure 3. Service request triggered by the UE. When data traffic is emitted by a UE in ideal state, the UE performs the procedure illustrated in figure 4. Firstly, signaling related to RRC connection setup is sent interactively between UE and ENB, which are reserved for the traditional procedure after the connection is established. UE sends a service request to global controller passing through the ENB. Next step, global controller process this request involving MME module and GNU and respond initial context setup request to ENB. At least after ENB sends the security setup and RRC connection configuration to UE. It can forward the data flow coming from UE to XGW. Meanwhile, global controller processes the flow table request and distribute new flow table entry which can steer data flow from UE to PDN to each XGW. Yes. Thus all connectivity setup in the control plane and the user plane, allowing the UE to receive and send data traffic. Simulation results and analysis. In this section, we evaluate and analyze the performance of the above system model as well as compare the numerical results of signaling load related to different applications scenarios in no stack architecture and in traditional T architecture respectively. About our physical scenarios parameters, setting the value of our density is set to 2300 UE per square kilometer and the scope of service area of the system including no stack and LTE is set to 1300 square kilometer. We analyze three types of applications and detailed settings are shown in the table 1. Furthermore, we propose four application scenarios. For first one is all default barrier scenario, which only uses default barrier to support all types of applications. The last scenario need multi-level QoS guarantee. The second scenario assumes the voice is supported by dedicated barrier, while media streaming and background applications still are supported by default barrier. In the third scenario, 10% of streaming and voice traffic are supported by dedicated barriers, while 90% of streaming traffic and background are supported by default barrier. In the fourth scenario, total voice and media streaming are supported by dedicated barrier, while background is supported by default barrier. The barrier inactivity timer is usually set to 20 seconds, and we also vary the RSC inactivity timer from 0 to 90 seconds so as to observe the influences and on the signaling load.